What happens if your Tesla runs out of juice in the middle of a deserted highway? No charging stations, no roadside assistance, just you and a $50,000 machine that has suddenly become a paperweight. This isn't just a minor EV glitch. It is the fundamental physical limitation of the entire industry. But in October 2025, a research team in China announced a breakthrough that could eliminate that barrier. A battery capable of self-healing from within, pushing its operational range past the 1,000-kilometer mark on a single charge. And if this technology truly makes its way out of the lab, the global EV game has already changed. The 21st century marks a pivotal shift in the transportation industry. In less than a decade, electric vehicles have evolved from a niche segment into a global phenomenon, experiencing unprecedented growth. After approximately 2 million units sold in 2018, the market surged to over 14 million in 2023 and is approaching the 20 million mark in 2025, with China alone accounting for over 60% of total global sales. But electric vehicles face a persistent dilemma: the battery. Over time, every lithium-ion battery system degrades due to physical transformations within its material structure. After approximately 1,000 charge cycles, capacity can diminish by 20 to 30%, significantly reducing the vehicle's driving range after only a few years of use. To understand this, we must examine the core challenge of solid-state batteries. When a battery operates, its internal layers expand and contract, much like a sponge being squeezed and released thousands of times. Over time, microscopic voids begin to emerge, much like hairline fractures on a road surface that develop after years of heavy use. Once these gaps appear, the flow of electricity is interrupted. Efficiency drops, the battery degrades faster. What is the traditional solution? Applying mechanical pressure, essentially clamping the components together to maintain surface contact. But that only addresses the surface. It does not prevent internal fractures from continuing to form. This is where China's new technology diverges. Instead of using physical force to hold the materials together, they have introduced iodine ions directly into the solid electrolyte. It sounds simple, but the mechanism is remarkably sophisticated. As the battery functions, these iodine ions are not static. They migrate precisely to the failure points, the interfaces between material layers. There, they form a specialized interface layer that attracts surrounding lithium ions. Think of it this way: if the gaps in the battery are like potholes on a road, this iodine layer acts as a 24/7 road crew. Any damage that appears is immediately filled before it has the chance to spread. No system downtime is required, and no external intervention is necessary. Crucially, this process is not a one-time fix. It repeats continuously throughout the battery's lifespan. It transforms the internal structure into an adaptive system that accommodates deformation rather than being destroyed by it. From an engineering perspective, this represents a significant shift in philosophy. Rather than attempting to create a perfect, immutable structure, which is virtually impossible at the material level, engineers have accepted change as an inevitability and designed a system to control it. It is the difference between an absolutely rigid structure and one that can flexibly adjust to applied force. The latter is not necessarily stronger, but it is undoubtedly superior. Initial test data show that this iodine interface maintains structural stability over hundreds of charge-discharge cycles without any significant loss of connectivity. If this mechanism is scaled to an industrial level, it won't just increase battery longevity. It will change the way we design energy storage systems entirely. When purchasing an electric vehicle, what matters most to you? Aesthetics, speed, or performance? Manufacturers, however, have a very different set of priorities. In the current EV market, most of the competition still centers on a familiar metric: capacity and range. Brands continuously push the envelope to 500, 600, or even 700 kilometers per charge to gain a competitive edge. But the real issue isn't what the car can do when it is brand new. It is how long it can maintain that performance. Then there is the matter of charging infrastructure. Even in the United States, where Tesla's supercharger network has expanded to over 50,000 stalls, fully recharging an EV still takes tens of minutes under optimal conditions and can stretch into hours using standard chargers. Bonus: in current lithium-ion battery systems, performance begins to degrade almost from the very first cycle. After approximately 1,000 charge-discharge cycles, capacity can drop by 20 to 30%, causing both range and operational capabilities to fall short of their original specifications. This creates a distinct paradox. The more advanced the technology, the faster its value depreciates over time. To address this, automakers and laboratories worldwide have invested tens of billions of dollars in solid-state batteries, a technology expected to deliver higher energy density, improve safety, and longer lifespans. However, over hundreds of cycles, materials expand and contract, creating microvoids that gradually reduce connectivity. Fundamentally, this weakness stems from the internal battery architecture, in which electrode layers and electrolytes fail to maintain perfect contact during material fluctuations. This is the Achilles heel that prevents solid-state batteries, despite their promise from achieving long-term operational stability. However, self-healing iodine-based interface technology operates on entirely different principles. Rather than attempting to maintain structural stability through mechanical force, this system is designed as an open architecture. Iodine ions are integrated directly into the solid electrolyte, acting as a dynamic intermediate layer that continuously adjusts and reconnects the interfaces between internal components. As the battery operates, iodine ions migrate under the influence of the electric field, concentrating at contact zones. There, they form an interface capable of attracting and retaining lithium ions, filling microvoids as they form. This maintains a continuous ion conductive network throughout the battery structure. No fractures, no interruptions over time. Consequently, internal resistance does not spike as it does in traditional designs, and energy flow remains stable even after numerous cycles. This creates a profound difference. The battery no longer hits its peak performance only at the factory gate before inevitably declining. Instead, it maintains a stable state for a significantly longer duration. To put it simply, a traditional battery is like a structure that loosens over time, where contact points become increasingly inefficient. The iodine technology is like a system that constantly tightens itself from within, keeping the entire structure in an optimal state. In the automotive industry, this isn't just a technical matter. It's an economic one. The true cost of an electric vehicle is not measured at the moment of purchase, but 5 to 10 years down the road. A battery system capable of maintaining stable performance means the vehicle doesn't lose its range prematurely, users aren't forced into early battery replacements, and the car retains its long-term utility value. According to test data from the Chinese Academy of Sciences, battery prototypes using this iodine interface structure remain stable after hundreds of cycles without significant physical degradation. A small detail, but one with massive implications. By optimizing the internal architecture, the battery pack design can shift toward a simpler form, eliminating the mechanical compression systems previously required to maintain interlayer contact. It is this specific detail that unlocks the challenge of mass commercialization. In battery designs, particularly solid-state variants, maintaining internal pressure is essential. Without sufficient compressive force, the contact surfaces between the electrodes and the electrolyte quickly delaminate during operation. This forces manufacturers to integrate heavy containment frames, tensioning systems, or mechanical reinforcement layers, making the battery pack significantly bulkier, heavier, and more complex to assemble. But with the iodine interface structure, the role of these systems is almost eliminated. Instead of utilizing external force to maintain stability, the battery sustains its own structure internally through a continuous reconnection mechanism at the material level. The iodine-rich interface acts as a flexible buffer, ensuring uninterrupted surface contact throughout the operational lifecycle. This means the battery pack's physical design can be streamlined, with fewer mechanical components, fewer potential points of failure, and greater integration with existing EV platforms, without requiring a total architectural overhaul. This is a highly practical advantage. In the automotive industry, where every design change incurs billions in costs and directly impacts production lines, a technology is only truly valuable if it can be plugged into the current system without causing significant disruption. And that is exactly what this technology aims to achieve. According to Professor Wang Chunsheng of the University of Maryland, a leading expert in solid-state batteries, this research addresses the primary bottleneck in next-generation batteries. The challenge is not just performance, but also the ability to achieve mass production at reasonable costs and with high stability. Without the need for complex mechanical structures to maintain pressure, the manufacturing process can be significantly simplified, from assembly to quality control, as the number of variables to monitor in each battery pack is drastically reduced. Fewer components mean fewer errors. Fewer errors lead to higher yield rates, and that is the decisive factor in large-scale production. Beyond design and manufacturing, this technology directly impacts the supply chain, one of the greatest pressures on the EV industry today. By extending battery life without increasing material inputs, resource efficiency across the product lifecycle is significantly improved. This means the demand for critical metals like lithium, nickel, and cobalt can be reduced per unit of utility value. Less material per life cycle, but more value per kilowatt hour. This is a systemic shift. As resource efficiency increases, not only do production costs drop, but the pressure on the global supply chain, from mining and refining to logistics and recycling, is also alleviated. At this stage, battery technology is no longer a purely technical narrative. It has become an industrial equation. In the EV race, the advantage does not just belong to whoever has the best technology on paper. It belongs to whoever can manufacture that technology faster, in greater volume, and at a lower cost across millions of units per year. And in that context, with an established supply chain and arguably the world's largest mass production capacity, China is not only capable of developing this technology, while the United States and Western nations have funneled tens of billions of dollars into next-generation batteries, focusing heavily on maximizing energy density, improving performance, and pushing material limits, most solutions still revolve around controlling the architecture through complex mechanical systems. These designs require high-pressure stabilization, hyper-precise manufacturing environments, and rigorous quality control at every microscopic level. The result is impressive laboratory benchmarks, but the trade-off is a sharp increase in production costs, extreme technical complexity, and commercialization timelines that stretch far beyond initial expectations. This creates a widening gap between on-paper technology and market-ready reality. In essence, they are attempting to build a perfect system by imposing external control. In contrast, China's approach to iodine interface technology follows a nearly opposite logic. Instead of trying to prevent the material from changing, they have designed the materials to adapt naturally during operation without destabilizing the system. By shifting the problem to the chemical level, the ions themselves maintain structural integrity and alignment over time. This doesn't just simplify the design. It creates a massive advantage when moving out of the laboratory. When these two philosophies collide in the real world, the scale of the ecosystem becomes the ultimate decider. As of 2025, China accounts for over 60% of global EV sales with more than 20 million vehicles on the road, while the United States stands at approximately 4 to 5 million, in Europe at roughly 8 to 9 million. This means China possesses a real-world laboratory larger than the rest of the world combined, where every vehicle is not just a mode of transport but a data point used to optimize technology in real time. The disparity is further evident in the charging infrastructure. China currently has about 1.8 to 2 million public charging stations, while the United States has only 170,000 to 200,000, and Europe has approximately 500,000 to 600,000. This creates a dense network that allows new technologies to be tested and deployed much faster under actual operating conditions. This doesn't just affect the user experience. It directly dictates the speed at which any battery technology can be verified, optimized, and scaled. When a technology is both mass production friendly and deployed within a superior ecosystem, it doesn't just gain a speed advantage, but the power to define global standards for the entire market. The winner won't necessarily be the best technology on a spec sheet. It will be the technology that can be deployed the fastest at the largest scale, and that is where the game truly changes. According to recently published empirical data, implementing an iodine interface battery architecture has yielded staggering results, increasing total energy storage capacity by up to 86%. More impressively, this technology pushes energy density beyond the 500 watt-hours per kilogram benchmark, a figure that represents a monumental leap over the 250 to 300 watt-hours per kilogram range currently found in high-end commercial lithium-ion batteries. However, the true significance of this breakthrough does not lie solely in these peak performance figures. In the world of high-capacity energy storage, achieving such density is often a glass cannon endeavor, powerful but fragile. The critical factor is that these metrics are achieved without compromising the system's fundamental stability. In conventional battery architectures, there is a direct, destructive correlation between density and longevity. As more energy is packed into the same volume, the mechanical stress on the internal materials increases proportionally with each charge cycle. This leads to surface fracturing, delamination of the layers, and the formation of high-resistance zones. These microscopic dead zones are the primary drivers of performance degradation, effectively acting as an inescapable physical ceiling that has constrained the industry for decades. The iodine interface addresses this breathing problem at the molecular level. Rather than fighting the natural expansion and contraction of the materials, the iodine ions act as a dynamic, self-correcting medium. They actively navigate the internal environment, facilitating the migration of lithium ions to fill microscopic voids as soon as they emerge during operation. This ensures that the ion conductive network remains seamless and uninterrupted, regardless of how much the battery is used. Consequently, internal resistance, the silent killer of battery efficiency, remains remarkably stable. Unlike traditional systems, which cause impedance to rise progressively until the battery is rendered useless, this self-healing mechanism keeps the battery's internal plumbing clear. Empirical data from the Chinese Academy of Sciences confirms the robustness of this design. Prototypes have demonstrated the ability to maintain near-perfect structural integrity across hundreds of extreme charge-discharge cycles without significant degradation. This signals a shift toward a system that is not only more powerful but also inherently more durable throughout its entire life cycle. Further expanding on its real-world viability, reports from the Institute of Metal Research highlight a secondary, equally vital breakthrough: the integration of a flexible polymer framework. This specialized structure enables the battery pack to withstand up to 20,000 mechanical bending cycles without any measurable loss in performance. This level of flexibility demonstrates a superior ability to manage the constant vibrations, thermal expansions, and structural deformations encountered in high-speed travel or heavy industrial use conditions that would typically compromise more rigid traditional designs. When integrating these advancements, it becomes clear that we are witnessing more than just an isolated improvement in capacity. This is a systemic upgrade across the three core pillars of battery science: energy density, structural stability, and ion transport efficiency. It offers higher density without the traditional sacrifice of longevity, and a more resilient architecture without compromising energy throughput. Most significantly, it signals the end of an era where battery performance was destined for an inevitable and rapid decline. This self-healing battery technology is more than just a technical milestone. It is the catalyst that could drive electric vehicles to eclipse the internal combustion engine far sooner than anyone anticipated. Beyond its technical scale, it establishes the electric vehicle as a transport solution with undeniable advantages. Operational costs could be 40 to 60% lower than those of gasoline-powered cars, while maintenance requirements could drop by as much as 30% due to the simplified mechanical architecture. Furthermore, carbon emissions at the point of use are virtually eliminated, providing critical relief for the environmental footprint of major urban centers. If a 1,000-kilometer range and a battery with near-zero degradation become the new industry standards, how much longer do you believe the era of the gasoline engine can truly last? Share your perspective in the comments below, and don't forget to subscribe to Massive Tech to stay ahead of the innovations defining our future.